So if we focus on this particular system, this is a monoatomic gas, single particles. So what are all the things that this single particle can do? This single particle can move in 3 dimensions, x, y, z. A single particle of a gas has no internal structure. This is all that it can do. So it can move in 3 independent directions. So this is something that we call as degrees of freedom, or the short form for this is DOF. So for a monoatomic particle, the degrees of freedom are 3 in number. Next, let us look at more complex molecules. So if we have a molecule like this is a diatomic molecule. Now diatomic molecules can do more complex things. This diatomic molecule can rotate about this x-axis, it can rotate about this y-axis, or it can rotate about this z-axis. About the z-axis, these molecules, the particles of these molecules are very tiny. So about the z-axis, both the masses are basically located on the axis itself. So the rotational inertia of this system is almost zero, very little. Rotational inertia depends on the distribution of mass. It takes very little torque to rotate this molecule about this axis. Very easy to rotate it like this. All the mass is concentrated on the axis itself. So this degree of freedom does not count. So the number of degrees of freedom of a diatomic molecule are, the rotational degrees of freedom are 2. So let us write down the entire degrees of freedom. So DOF, degrees of freedom. For monoatomic degrees of freedom are 3, and these are translational degrees of freedom that come from motion. Translation means motion, the shifting, not rotation. Movement without rotation is called translation. For a diatomic gas, the degrees of freedom are 3, which are translational, plus 2, which are rotational. Now if we consider a triatomic gas or a polyatomic gas, the number of degrees of freedom will be 3 translational plus 3 rotational. Let us look at it why. If you look at a triatomic molecule, let us say this molecule, there is another molecule here. Now if you rotate it about this axis, this molecule will have significant rotational inertia because it is far from the axis. These particles are on the axis, this is far from the axis. So this rotational, this degree of freedom will count. So the number of degrees of freedom of a triatomic molecules are total 6. 3, 5 and 6. Apart from this, there could be other degrees of freedom. A molecule basically can do other things. A diatomic molecules, it can vibrate also. These are other things it can do. Basically now we know from quantum mechanics that this degree of freedom only gets activated at very high temperatures. So we need not count this degree of freedom. Apart from this, molecules can do more complex things, but we don't need to count them. They are not in your syllabus. We will study such oscillations in the next chapter. These degrees of freedom don't count. We could have more degrees of freedom like this. More complex things. But these things happen only at very high temperatures, and we won't be studying molecules in that regime. These are all the degrees of freedom. Now, after we have written these degrees of freedom, if we look at a gas, here we have diatomic molecules which hit and collide. So after sufficient amount of time, the velocity is randomized. So if we look at these molecules, what all they can do? These molecules can move as well as rotate. They can move also and they can rotate also. So the question is, what is the relation between the translational energy and rotational energy? They are moving as well and rotating as well. So there is a very powerful theorem of Boltzmann, which is the soul of this particular chapter. It's called the equipartition theorem. These molecules can move as well and they can rotate as well. So let us write down a result which quantifies how fast are they moving and how fast are they rotating.
So degrees of freedom is apart.
This is called as equipartition theorem. Equipartition theorem says that each degree of freedom in thermal equilibrium contains an energy equal to half kT on average. So what this is saying is that whether that degree of freedom is translational, whether that degree of freedom is rotational, each degree of freedom receives the same amount of energy, which is half kT. T is the temperature and K is a constant known as Boltzmann constant. This is equipartition theorem. Each degree of freedom receives an energy which is equal to half kT on average. Now finally, using this we can write down the formula for internal energy of gases. First, let us consider monoatomic gas. Monoatomic gas, n particles. Diatomic gas, n particles. Triatomic gas, n particles. All of them are at the same temperature T. Total internal energy of this gas, which is also the total kinetic energy of the gas, because the molecules are not interacting with each other, otherwise we could have potential energy as well. They only have kinetic energy. Each degree of freedom gets half kT. In monoatomic gas, what is the number of degrees of freedom? 3. This is the average energy of one molecule, and there are capital N molecules. So this is the formula for internal energy of a gas, 3 by 2 nKT. For a diatomic gas, each degree of freedom receives half kT. The number of degrees of freedom of a diatomic gas. First, there are 3 degrees of freedom for translation and 2 degrees of freedom for rotation. So total number of degrees of freedom is 5. This is the average internal and average kinetic energy of one molecule. There are total n molecules, so we will multiply it by n. This is 5 by 2 nKT. Internal energy half kT. The degrees of freedom for this is 6. So this is 6 by 2 nKT or 3 nKT. So we can write down a general formula for internal energy. It is each degree of freedom receives a half kT. We can label degrees of freedom by the letter F. Number of atoms is capital M. So the formula is F by 2 nKT. This is the formula, first formula for internal energy of a gas. F is the degrees of freedom. What is F for monoatomic molecule? 3. For di? 5. For triatomic?